Okay, so today I'm going to talk about solution formation. So we're going to kind of talk about the mechanics of how solutions form and some of the effects that has on solubility and what we observe. So a couple quick terms I want to throw out there. Concentrated solution. Now this is a general term. There's not a numerical value associated with the idea of a concentrated solution. Concentrated solution is just one that contains a large amount of solute relatively. So it's sort of like the terms big and small. They're relative, right? It depends what we're talking about, compared to concentrated, compared to what. So it's a judgment call, basically. Same thing with dilute solution. A dilute solution is the opposite. A dilute solution is one that contains a relatively small important terms are aqueous solution. So an aqueous solution means a solution where water is the solvent. Now, aqueous solutions are really going to be our most common. We're going to deal with aqueous solutions mostly. We're not going to deal with non-aqueous solutions that much. So non-aqueous solution is where something other than water is the solvent. So there's a couple quick definitions out of the way. Let's talk about how solutions form. Now, I'm going to talk mostly about dissolving things in water, but we'll need to talk about dissolving things in other solvents as well. So there's the way a solution forms. So if you imagine at first, if I mix two things together, so let's say I have salt, which I'm going to just draw as little, actually let's say it's sugar. So my solute is just sort of sitting in solid form at the bottom of a beaker. And then I'm going to add a bunch of water on top. Before anything is added, or at least before anything mixes, right? Why is the sugar a solid at room temperature? And the answer is because it has strong intermolecular forces. The intermolecular forces are pretty strong, right? And this is a liquid at room temperature. The intermolecular forces are also pretty strong. Now we know that water and sugar mix pretty well. But imagine, so there's this boundary here between the solid and the liquid. Now in order for this to interact, in order for the solute to dissolve in the solvent, what has to happen, so we're trying to get from there to here, where we have, solvent mixed all in and solute mixed all in is what we're trying to get to. So imagine it happening in these steps instead. Imagine that instead I have to first, step one, I have to, so here's my solute down here, right? Now imagine that first I have to pull apart the solvent to make room for the solute, right? So imagine I have to yank it apart. So I have to overcome that attraction, because what's going to happen is the solute's going to try to put itself between water molecules. So it's got to split that force. It has to divide the water, right? So it has to overcome that intermolecular force. Now, the next thing that has to happen is, in order for the solute to mix in, it also has to separate, right? It also has to separate it. It doesn't happen so weirdly cartoonishly like this, but just bear with me here. And then when we mix the two together, right, then they're nice and mixed together. So it's going to take energy. It takes energy to pull these two things apart, right? Well, where does my driving force for that energy come from? And it comes from the attraction between the solute and the solvent. So, think about it in these terms. The two forces we have to overcome, the two interactions we have to overcome, are the intermolecular forces between the solute and the intermolecular forces between the solvent. So the attraction between the solute and the attraction between the solvent both have to be overcome. the primary driving force is the interaction between the solute and the solvent. So, in order for the driving force to be on par with the forces it has to overcome, so in other words, this driving force has to be stronger, as strong or stronger than these forces, right? So imagine I have, it's probably going to be the easiest to deal with thinking about two liquids, I think. So I have one liquid, I'm just going to draw them here as, let's say here is one liquid, and here's another liquid. Now let's say that the top one is nonpolar and the bottom one is nonpolar. Now, how difficult is it to, how strong is the interaction within nonpolar substances? It's pretty weak, right? So, in order to pull apart this substance, it's pretty easy, right? You can pull it apart easily because the interaction isn't very strong. This one also you can pull apart easily because the interaction isn't very strong. Now when you mix them together, they're not going to interact very strongly, but that's okay. They didn't have to overcome you didn't have to overcome much of an attraction to begin with. So things that are soluble, or things that mix, I guess I should say, things that mix, combinations that mix are nonpolar, right? That's one of them. Let's say that they're both polar, right? Let's say they're both polar. Well, how hard is it to pull apart pull apart the molecules of a polar substance? It's much harder. It's a lot harder. So you have to pull this substance apart, and it's really hard. You have to pull this substance apart, and it's really hard. However, because they're both polar, they're going to interact really well, right? There's going to be a lot of interaction between the dipole-dipole bonds and of each. And so, though it takes a lot of energy to yank these both apart, the interaction is going to be very good because they both have these dipole ends to mix and match. So polar works well. Now let's talk about what doesn't mix. What if I make this blue one nonpolar? If the blue one is nonpolar, then it pulls apart really easily. I can easily pull the blue particles apart, right? The red one is a lot harder. There's a lot of energy to pull apart. And now if we look at the blue particles, they're neutral. The red particles have positive, negative, right? So the interaction between something that just has London forces and something that's polar is not going to be very good, right? There's no real, they can, but it's not going to work really well. This would be fine if both of the substances were easy to yank apart, if all the interactions were equally, weak. But they're not going to mix well. So I'm going to call this nonpolar, polar. And the reason is, another way you can think about it is, what would the molecules rather do? Would the molecules rather hang out with themselves, their own kind, or mix with each other? So when you have nonpolar, there's not really a difference, right? It doesn't really matter if this nonpolar molecule is mixing with that nonpolar molecule or that nonpolar molecule. It's going to hang out with both equally, so they mix well. Same thing with if they're both polar. But if one is polar and the other's not, then this polar molecule, this red one, fundamentally is going to want to stay around other polar molecules like the other red molecules. So they sort of create a barrier where the blue, you could mix the blue with other nonpolar things, but it's not going to want to mix together. So either, if you have a mixture of polar and nonpolar, they don't mix well. So this leads us to a general rule for molecular compounds, which is like dissolves like. And what I mean by this is that polar solvents dissolve in polar solutes dissolve in polar solvents, and nonpolar solutes dissolve in nonpolar solvents. Anyway, polar mixes with polar, and nonpolar mixes with nonpolar. This is why paint thinner works. Paint thinner works because paint is often oil-based, right? It's not water-based. So to get it to dissolve, you have to have something that's nonpolar. That's all paint thinner really does. There's no chemical reaction going on there. It's just, or paint remover or turpentine. It's just that they're dissolving the paint. That's it. They're just dissolving it. The paint still exists. It's still intact, right? And you can tell because the color stays the same. It doesn't change the color. It's just separating the molecules into a solution. And that's really it. Now, this rule holds well except in the case of ionic compounds, but I'm going to come and talk about ionic compounds in a minute. I'm going to talk about the solubility of them in a minute. I want to talk about the mechanism of how ionic compounds dissolve, because there's something special and different that happens with ionic compounds when they dissolve. So, not special to ionic compounds, there's, you could say that hydration is something that happens with everything that dissolves, but ionic salts do something very special. So, water is polar, right? Water is very polar. It's got hydrogen bonding, it's got a very negative end and a very positive end. So when you remember that ionic compounds don't exist as molecules, they exist in a lattice, right? This repeating structure of positive and negative ions. So what happens is, fundamentally, basically, if you want to know if something dissolves, think about this. Does the thing dissolving, does the solute, have more attraction to the solvent or to other molecules of the solute? Now, in the case of ionic compounds, what we're talking about is now we're going to talk ion by ion. Does this ion have more of an attraction to the water or to the ions? Now, water is really polar, so I'll tell you this. Nonpolar substances, nonpolar solvents, aren't going to have a chance of dissolving ionic compounds. Because remember, what's holding ionic compounds together is the charges. But if you get enough little water molecules hanging around, right, and they all point the negative ends at the positive ion, and they'll tend to do that because of the attraction, what can happen is now this positive ion kicks loose and then is able to be surrounded by lots of water molecules, and it's happier that way because there's more attraction that way. This now exposes these negative ones, and not the same water molecules, but more water molecules come along, and now they show the positive end, the hydrogen end, and they surround the ion and they separate it. So what happens with ionic compounds in solution is they undergo a process called dissociation. Oops. So when I say the word dissociation or dissociate, this means that the ions are falling apart. The ionic compounds fall apart to form individual ions. Here's a better image than I can draw. So you see the water molecules coming along and taking this negative ion and taking it away, and this positive ion going away, this cation going away with the water molecules. So, from ionic compound to ionic compound, it really depends. Are the ions more attracted to the other ions of the opposite charge or the water molecules? And this can vary a lot from ion to ion, but I'll say this. Water is one of the few solvents that's going to have a prayer of dissolving ionic compounds. Most other solvents aren't polar enough to do it. So, when an ionic compound dissolves, it breaks into its component ions. So, what's important to understand is when you see sodium chloride, a solution of sodium chloride, it's not really sodium chloride, right? Sodium chloride is salt. It's a solid, right? The ions are stuck together. What you really have in solution when it's dissolved are sodium ions and chloride ions. They separate apart, right? The ionic compound blows apart. Magnesium chloride would have magnesium and chloride. But one thing that's important to know, you'll have twice as many chloride ions as magnesium chloride units, right? And the reason, it's important to note also that here, this is a subscript. This, on the chlorine, there's a subscript indicating that in this unit, all packaged together, is a magnesium ion and 2 chloride ions. But now that they're solvated, now that they're hydrated, solvated is the general term for being surrounded by solvent molecules and dissolved. Hydrated is specific to water. So now that they're hydrated, the ions are separated. So this is 2 totally distinct and separate chloride ions that don't hang together as like Cl2, right? Okay. So here's the solubility rules I talked about earlier. Ionic compounds, it works very well. And we're going to kind of come back to that, but I want you to know that ionic compounds fall apart. Another thing that's really critical, if you consider sodium sulfate, it's going to dissociate into 2 sodium ions, and 1 sulfate ion. The polyatomic ions don't further dissociate. They don't break apart into sulfur and oxygen, right? Those are covalently bonded. They don't separate like that. The ions, the polyatomic ions, the reason we think of them as whole units like that, as whole bits, is because in water they separate out into SO4, right? It's just sulfate. Okay. So ionic compounds, there's no real way to determine the solubility of an ionic compound just by looking at the structure. You can't just look at it and say, oh yeah, sure. Now, I just realized something. Okay, this is this is from the older version of your book. The one in your book is prettier, but it has the same information. And it's structured basically the same way, except there's some nice lines to help you delineate. And it's the newer version that I will give you on an exam or quiz. So you do not have to memorize this. I'm going to say that again. You do not have to memorize these solubility rules. These will be given to you if you need them. Okay. So here's how you read the chart. If you want to know if an ionic compound is soluble in water or not, so this is specific to solubility in water, not other solvents, you try to find one of the ions on the left side of the chart, one of the ions in the compound. So if I give you sodium chloride, NaCl, you would look and find, oh, sodium right here, group 1A. Great, great, great. There it is. And there's 2 parts to the, right, there's 2 parts here to the chart. These are things that tend to be soluble. So what the chart is telling you is that sodium, compounds, ionic compounds containing sodium, tend to be soluble. Over here are any notable exceptions. There are none. Sodium has no exceptions. Sodium anything is soluble. There are actually like 4 categories here that have no exceptions at all. And while I said you don't have to memorize them, if you can remember that group 1A, ammonium, acetate, nitrate, those are always soluble, you'll save yourself a lot of time. Now let's take a look at like silver chloride. Chloride tends to be soluble, but silver is an important exception for it. Now, the way you read this, don't think that these are exceptions for all of these, right? There are no exceptions. They just directly relate across. So chloride, bromide, and iodide, they have, their exceptions are silver, lead-2, not lead-4, but lead-2, and this mercury ion. So AgCl is insoluble. Now, why did I put a little S after it when I said it was insoluble? Because I didn't say it was soluble. Because remember, the little S in the parentheses means solid, not soluble. So it's not going to be able to dissolve. It stays a solid. Now, down here are the insoluble compounds, like carbonate, phosphate, sulfide, and hydroxide. And they have notable exceptions, primarily group 1A and ammonium, right? And then a few others for hydroxide and some others for sulfide. Sulfide group, it doesn't, so sodium hydroxide, is this soluble or insoluble? Hydroxide tends to be insoluble, but group 1A, sodium is in group 1A. There's an exception, so it's soluble, which I'm going to call aqueous. I should really call this one aqueous too. Aluminum hydroxide, soluble or not? Hydroxide is usually not soluble, and aluminum is not an exception. So it's insoluble. So there we go.